Lumped capacitance. Welcome back, everybody. And we are in the third week of classes. We're midweek, and the first week we saw energy balances. That is essentially like balancing your bank account, money in, money out, interest rate. Those are your savings. Same with heat. Heat comes in, heat goes out. Some heat can be generated, and that is our energy balance. That is the heat stored. We saw that it can be done as a batch in joules. We saw that we can do it in as rates in watts. And we, during the first week of class, we said nothing about how the heat comes in or how the heat goes out. Then in the second week of class, we said, okay, let's look at the how heat comes in and out. And without getting into the physics of it, which we will do later on in the class, we went into the, look, direct heat transfer by convection or radiation or contact. All those three go through surfaces, or by conduction that happens inside the body. And we gave little, very, very simple formulas for those and ballpark values, like saying there are two types of convection, like natural convection, that is the convection driven just by, for example, the hot air that is next to me. It moves up, and that creates a motion that has some fluid velocity, but is not externally imposed. That's natural convection. In gases is more or less 10 watts per meter square Kelvin. And if an external velocity is imposed, for example, by a fan or by wind, or if we are swimming by the velocity of water, relative velocity of water as we swim, that would be forced convection. And we said in the case of forced convection in air, we can expect a convection coefficient of the order of 100, and if it was liquid, of 1000. And that has helped us already to explain so many things. For example, why 20-degree weather sitting on a park is awesome, but 20-degree water is very cold to swim in. Why we need to eat 2,000 or 2,500 calories a day if we do no exercise, and if we do exercise, we would need to eat more. We learned that. And then we said in the third week is, let's put together these energy balances and these heat transfer mechanisms. Let's look only at the mechanisms in which heat is exchanged through the surface. That means let's keep conduction separate, because conduction is going to give us very difficult equations. Now, if we put together the energy balances of week 1, together with the heat transfer mechanisms of week 2, and in week 3, we make one hypothesis, that is, let's assume that the temperature inside the body is uniform. Everywhere inside the control volume, the temperature is the same. That happens to be almost exactly true in many, many cases. We don't know what those cases are yet. We will know what cases are next week. But let's say if you can say the temperature inside the body is more or less uniform, then you can do lots of calculations that are much simpler than the alternative when there are gradients. In this condition in which the temperature inside the body, the control volume, is uniform, is what we call lumped capacitance. And it is because all the thermal mass acts as if it was lumped into one single something. We don't need to worry about shapes anymore. Whatever the shape, all we need to know is how much mass and what specific heat we have inside. So here. So I'm going through the notes. By the way, I have people coming to the office hours, and I'm glad for it. I enjoy it. This is what I chose to do with my life. That said, is a much smaller fraction of the students that are in class. I invite you to come. I promise you that if you come, I'll be happy that you came, and very likely I'll be able to help you too as you try to understand the course material. This class has a special challenge that nothing in itself is difficult, but all of it together is very deep. So if you think you understand every part of the class, chances are that you're right, but that does not mean that you understood it all together. And in addition, this class will use material that you have seen in previous years that it's so long ago that you might have it rusty, right? Like ordinary linear differential equations, for which I already uploaded a math refresher at the bottom of the list of topics. Anyway, so what we did on Monday is to look at, let's see. What we did on Monday is to look at one example that was a sphere of 6 centimeters in diameter made out of copper, and that was initially at 90 degrees C. That means hot, really hot to the touch, and is in a large room without a forced wind, with air at 20 degrees C. And before we did any math, we knew that the final temperature of the sphere was going to be 20 degrees C, because everything we leave outside eventually it reaches the temperature of the room. That was easy, but it has important implications. Then we took it one notch up. We said, okay, how many watts are we losing at the beginning when the sphere starts to cool? And we knew, because we have, based on what we learned in week 2, we can see, it's losing heat by convection. I told you that in the statement of the problem. And I have a formula for convection. Plug and chug the formula, and we got it losing almost 8 watts, whatever those are. But then we said, okay, but what does it mean from in degrees per second? And then we said, okay. Very easy to know how many watts I'm losing, but to know how many degrees I'm losing, I need to see the relationship between heat content and temperature. And that goes through the Q stored. And then we needed to do a heat balance to calculate the Q stored, which was so simple to be trivial in this example. But this exact same equation can account for very complex problems, as I intend to see today and on Friday. So now, this we did last time. We did our energy balance, and here we have our control volume. We have the equation of energy balance. We replace the mechanisms of heat transfer. In this case, we only care about the Q out for heat transfer, and we have a Q stored, both of which we know from weeks 1 and 2. And we ended up, after we put those numbers together, we end up with this equation 13. That is extremely important, because as you see it already, this is a differential equation. Not that you love them, by the way, I do. I think they're awesome. But you don't have to think it's awesome. But you have to see how powerful this simple energy balance is, that ends up in generating a differential equation, which in this case, you have been taught how to solve, and is also in the refresher, and will let us calculate temperature at any point in time. Now, before we solve the differential equation, it's very important that we have a sense of where we are going. So we know this. We know that we start at 90 degrees at time 0. We know that was the statement of the problem. We know that at long times, whatever long is, but long, temperature will be 20 degrees and will not move from 20 degrees. Those things we know, right? And we also know that at the beginning, the sphere is cooling down at a finite rate. By finite, I mean, it's not 0 rate, cannot be a flat line at the start of the curve, and it's not infinite either. Whatever it is, it's not 0 and it's not infinite, right? And we know that because we did this calculation of what is the initial cooling rate, and we got that it said not infinite, we got a number, right? It was 1.21 degrees per minute. So before we solve the differential equation, we know we should expect a curve of this shape, right? We know that it started to cool down at a given slope here. We know it goes to a final stage that is flat. We do not know if in between this beginning and the end it's going to go crazy. But let me tell you something. I know it's not going to go crazy because I have solved the equation, as you will in a minute. And I know it looks exactly like this. But if you don't know, I suggest you assume that the way you connect the beginning and the end is with a curve as simple as you can. Because in heat transfer, things tend to be as simple as they can be. This is what is called a heuristic, a rule of thumb. Sometimes things can be crazy, but it's so seldom that I suggest you start thinking simple. Always think simple. Always think, if I knew nothing, what would I imagine? And based on what you imagine, then you can start getting more and more rigorous and more formal. Okay, so in this curve, I highlighted a concept. That is a concept that might be new to many of you, although you might have heard when you talk about half-life decay of radioactive substances, or if you have done any research, you might have heard people talking about full height, full width, half maximum, or things like those. And it's how do we attribute one single characteristic value, one single value to a curve that doesn't have any sharp point anywhere, right? If somebody asks you, how long does a sphere take to cool down? You have to give an answer. Engineers always give answers. And good engineers actually even give good answers, give answers that are useful. So what I have proposed, and I discussed this with you on Monday, and it's in the notes, is that we take the slope when the process starts, and we project the slope until it intersects the flat line of the steady state. The time at which this intersection happened, this is what we're going to call the characteristic time. That is the one time that we're going to use to represent the whole process. And because it's the slope, applying the definition of a slope, here we end up being able to calculate that this characteristic time was just shy of 1 hour in this example. Now, although if somebody asks us this question, how long does it take to cool? We give an answer, but we know that really cooling is to an infinite time. So a fair question is, all right, fine. In this time, you tell me, is it really all the way down to 20 degrees C, the sphere? No, of course not. Okay, to what temperature? At what temperature is it? I don't know. So if I really wanted to cool it down to 25 degrees C, how long would it take? How long would it take to cool down to 20.1 degrees C? Those questions you cannot answer so far because we got a characteristic time that is something kind of rough and ready, but with emphasis in the rough. To answer the question is of, okay, at the characteristic time, what is the temperature, or how long would it take me to cool down to 21 degrees? For that, we need to solve the differential equation. In this case, it's the simplest case that can be. I'm not going to say it's easy, because some of you might have traumatic memories of the time taking this topic. But I will tell you, it does not get any easier than this. So I hope you love it, because if not, there's no hope. Cannot be any easier. And here I grabbed the equation that I mentioned at the beginning, this equation here, 13, and I move the terms around so it looks like the differential equations you might have seen when you took your calculus class. And we already discussed, it has a first derivative here and not second derivative, so it's a first order equation, because the derivative and the variable is to the power of 1, is not a sign of temperature, it's not temperature squared or to the fourth. For that reason, this is a linear differential equation. It matters, because if it is not linear, you don't want to deal with it. But this is linear. And it has only one independent variable, that is time. So we're happy because it's an ordinary differential equation, the easiest type of actually, this is the only type of differential equation that can be solved. If you have partial differential equations, the only way of solving them is turning into ordinary differential equations. Of course, numerically, you can play other tricks. So we're good, and we're happy on this case, or we're as happy as we can be. And what else? We needed then one boundary condition, which we had the initial temperature, and we needed to do a change of variables, so it would turn into a non-homogeneous equation into a homogeneous equation. That homogeneous is when the right hand, when this part is 0, but in this case it's not 0. So we do this, and the equation in this new notation with this change of variables, which we did discuss on Monday, gives us this new equation that is the exact equivalent of this equation here. There is no simplification I have made. I had turned this that has lots of ink into this other one that has much less ink. And theta is the difference between, is what we can call a superheat temperature, is how much above the final temperature you are. And K was just a shorthand notation for this bunch of things here. We're going to see later what it is. Now, I didn't mention much of this on Monday, but we can, from this equation, we can see what the relation, how to predict the characteristic time. And we said characteristic time is when the initial tangent intersected the steady state temperature. And in this case, this is a case when we're in steady state. Sorry, this is the case in which we look at the derivative in 0, and the derivative in 0 is, I can solve here. I have the derivative and I have the value of the variable. I pass this to the right and I solve for it. And what do I get? That this characteristic time, right, ends up being 1/k. My suggestion is that when you have a minute, we have very few assignments in this class, and the reason is to give you time to practice things on your own without the pressure of having to be delivering things all the time. It would be very hard if you had to do lots of assignments, and in addition, trying to figure out these things in which I put in the notes, I'm saying now, but I know because I was a student too, I still need to do it myself. Okay, So the beauty of this is by looking at the initial slope, I can get a sense of the characteristic time. And the characteristic time that comes from the equation is given by this expression that has volume, density, specific heat, and volume and density is mass, surface area, and convection coefficient on the surface, right? We can now, if we have a lumped capacitance problem, and people ask us, how long is this going to take to heat up or cool down? Using the characteristic time as a ballpark value, here we have the formula for that characteristic time. That is power. Everybody knows that the sphere would cool down. Only engineers will know how long it will take. And only really good engineers, like I'm doing all my effort, so you are among those, will say, and I can give you an answer right now. That's cool. All right. So let's get into the favorite thing. Let's solve the differential equation. I'll show you the way I like to solve my differential equations. You can solve it any way you like. The way I solve the differential equations this way is because this way is also good for second order differential equations. And it is, I'm going to postulate, because I know it, I'm going to postulate that a linear differential equation of the first order has a solution that is an exponential, in which I don't know the coefficient in front of the exponential, and I don't know also the coefficient that multiplies the independent variable, in this case time, inside the exponential. So I have two unknowns here. What I'm going to do is I propose this. By the way, I didn't invent this. This is the way it was taught. And there are many other ways, especially for first order equations. So I can do the derivative of this, and then I replace this function here that I proposed, I postulated, and its derivative, that once I postulated the function, the derivative comes straight out. And I'm going to replace these two inside this equation we have here, equation 21. You have to do this on paper yourself. You look at this, and it all, I hope it all makes sense, but when you do it yourself, it makes a lot more sense. Okay, so I have a question here. Can we get practice questions from the textbook? Absolutely, yes. And as a matter of fact, in the syllabus, I listed exactly what practice questions from the textbook I recommend you look at. And in addition to that, if you go to eClass and you look at quiz 1, in which I already opened it up, of course, you can only take the quiz on Wednesday next week at the times that we have established. I'm saying also from the textbook what practice questions and what sections from the textbook to look at. In addition, on Monday, I uploaded every single assignment I gave in the past with the answer keys. And in addition, you have all the previous exams I ever gave with the answer key worked out by me or the TAs. And please take a look. If that is not enough and you like more, I am sure I can scrape the bottom of the barrel to find more and more problems. And I'll be happy to discuss on Friday during the office hours. Okay, so we replaced the postulated function, the derivative into the original equation, and I can, as long as C1, the exponential is never 0, so I can cross out, and C1, as long as it is not 0, I can also cross out, and I end up that R equals minus K by solving this equation here, 29. And interestingly enough, remember we said that K was one of the characteristic time. Interesting, so we have it here. So we already, of the two unknowns we had, one was C1 and the other was this coefficient R. We just solved for R. And from the boundary conditions, we're going to solve for C1 because at time equals 0, this function theta of time 0 is C1. And we knew that at time equals 0, we had written it down. Time equals 0, theta equal theta 0, that was T0 minus T infinity. So we have just solved the differential equation in a very general way. And that's part of the cool thing of studying lumped capacitance. It applies to so many different problems, not just spheres cooling down, but equipment. If you ever wondered how long does it take, you drove to some place in the winter, your engine is warm. You know that if you come back soon, you go to buy groceries. You know if you come back soon, the engine is still warm and you're a happy person. You know if you take too long, the engine is going to be cold and it's going to be more difficult to restart. How long does it take for the engine to get cold? You know what? That is a good lumped capacitance problem. And many more, both in materials engineering, petroleum engineering, chemical engineering, mechanical engineering that has the same class but taught separately. So if that, I now expand, because this notation was somewhat cryptic, right? And we had theta and things like tau. So we have now temperature as a function of time is T infinity, that is our steady state temperature, the temperature of the fluid. We multiply by the initial temperature difference. And here we have an exponential decay. And if I expand this tau here, this time constant, we get this expression that involves the surface area, involves the convection coefficient, the volume, the density, and the specific heat capacity. Look, in this equation, you already see some really cool things. For example, those of you who have children or have nephews or young siblings, you know that babies can suffer the cold much more than adults. Why? Here's the answer. Babies are very small, and for that reason, the surface area to volume also becomes very large. Sorry, the surface area, yes, surface area to volume becomes very large. That means for each kilogram of flesh, they have more area to lose this energy outside. A baby can get hypothermia much faster than an adult. That comes in these equations we're seeing here. And of course, this also applies for transient questions of how long might it take for a heat exchanger to reach steady state, or how long can it take for my engine to cool down. These can be applied to how long does it take for the engine to warm up. There are two examples I want to discuss. One today for sure, and one likely is going to be on Friday, is how do we make snow in Snow Valley when they use these big snow blowers, right? That the snow makers. Let's talk about that, because that's a lumped capacitance problem. And the other, for those of you who are into gaming and you are familiar with overclocking your chips or using spatial refrigeration, let's discuss the time constants associated with chip thermal management and what happens in case of failure. All right. Here I discussed something that I'm going to leave for you to read, but we can do lumped capacitance with radiation too. And the differential equation we end up with, I'm going to highlight only one thing. This equation is very similar to the one you saw before, except you see temperature is temperature to the 4th power. This equation is not linear. This equation can be solved. It's not too difficult, but it's way more difficult than the previous one. The book has it worked out. I'm not too excited about doing math for the sake of math, but I wanted to show you that, yeah, it can be nonlinear, so you know what it is, that we can apply it to radiation. And something that the book doesn't say, but is that if we use the equivalent convection coefficient for radiation, then we can like fake it and solve radiation as if it was convection. It's not going to be exact, but in some cases it's going to be close enough. So you know, if you look in the book, you have the exact solution for the radiation problem, and there are ways of going around it, because in the end, with radiation, you're also going to end up at room temperature, or temperature of the surroundings, right? And you're going to start losing heat. The curve looks very much the same. It's not, but looks like very much the same. Snowmaking. So let's say, I just realized, snowmaking. I want to make sure I'm saying things right. Okay, good. How does a snowmaker work? Things are a little bit only slightly more difficult than I make them here. But essentially, you have these big fans surrounded by water jets. Now, first of all, the air has to be cold, right? And you know, because now you know so much about lumped capacitance, you know that the droplet that you spit out of the nozzles will be at the temperature of the surrounding air. So the surrounding air better be below freezing, right? And the lower below freezing, the better, because somehow you need to freeze them in the air. The one thing I'm not going to discuss much is that the water you put like agents to nucleate the ice quickly, because there is, those of you might know this for sure, and I believe those in chemistry and petroleum might have been exposed to this concept too of nucleation. Water doesn't turn into ice exactly at 0. Sometimes you have to undercool it a little bit, right? And they use seeds for this nucleation. But in this class, we're going to assume that the water freezes at 0 degrees directly. So the question is, how long does it take until a droplet can be completely frozen as it flies through the air? Amazing question. Why does hot water freeze faster than cold water? I did research into that. So let me tell you, this phenomenon has a name of a guy who came up with it. I think it was a guy in Africa, actually. I don't remember the name. But it's not certain that this is a fact, that hot water freezes faster than cold water. People have done scientific experiments about this, and the evidence is inconclusive. That sometimes, yes, hot water seems to freeze faster than cold water. Sometimes it does not. If you look it up, I think there's a Wikipedia entry there, and people don't necessarily agree. Those who propose that that hot water freezes faster than cold water, they use theories that don't persuade me very much, because they invoke very weird phenomena, none of which is a phenomena that we deal with in this class. It's none about radiation or convection or conduction, or not even about nucleation and growth. So hey, here you have something to discuss on Friday office hours if you wish, because I think it's really cool. Right now we can do the experiments ourselves. We have a cool thermal camera in the lab too, where we could track the droplets. if we wanted. But if you ask me, yeah, we haven't mountain weather, yeah. But now if you ask me, I believe it's not true that hot water freezes faster than cold water. Yeah, you can account for evaporation too. None of the theories is a theory that has been widely accepted yet. Anyway, going back now to our class, this is a similar topic. We spit the droplets out. How long does it take until the water froze completely? So in this example, I'm assuming it's -20 outside. I'm assuming that the droplets are spit at more or less 6 degrees C. And I'm also assuming that the droplets are 0.5 millimeter in size. I think I way overestimated the size there, because if you look at the nozzle manufacturers, tell you a nozzle with a given pressure, what size of droplet is going to eject. In this case, I assume something, but I think I assume too large. But we could look into that too. If any of you wants to look into nozzles and tell it to me, I'll redo the problem in a more realistic way. I'm assuming here for the small droplets a convection coefficient of 200 watts per meter square Kelvin. Typically, I would have said 100, right? Because as the droplet moves to the air, that would be forced convection. But 200 is more realistic, and you will see that because you will know how to calculate the exact number a few weeks from now. We are going to have two stages in this problem. Stage one, you spit out from the nozzle water at 6 degrees C and starts to cool down, but it's always a liquid until it starts to freeze. Between the moment the droplet comes out of the nozzle until it starts to freeze, I'm going to call that stage one. Then once the droplet starts to freeze, it's going to freeze more and more and more and more until it's completely frozen. That's stage, I'm going to call it stage two. And that is a question, how long does it take to be completely frozen? Do you realize that if the droplet doesn't completely freeze, we're going to have a whole bunch of wet snow. It's going to be like quite ugly, right? So very practical problem. And this is exactly what it is, right? I just took out the little effect of nucleation agents, which actually would not affect the answer very much. And let's look at this. So we want to calculate this total time. Time one in stage one plus time to solidify in stage two. First stage, stage one, cooling of the liquid droplet. You don't know if you can or not, but I'm telling you that you can assume that the droplet is in uniform temperature, spatially. You will be able next week to tell me if it is true or not. But yes, you'll see it's very, very true when the droplet is so small. So we can go back to equation 33, which you do not need to memorize. You do not need to memorize. But equation 33 is the exponential decay. Here we go. This is our exponential decay. And we have to solve for time. This time one, as the droplet cools down with uniform temperature and no phase changes, we're asking, we know that the droplet came out at 6 degrees, will start to freeze at 6 degrees, right? So it starts at 6 degrees, finishes at 0 degrees. The outside temperature, T infinity, was -20. Here's the initial temperature, that is plus 6 degrees. T infinity we know, and this tau, right? That is the characteristic time, the time constant, have this expression, which you do not need to memorize. If you were taking the class normally, that would be in the formula sheet. But what really matters to me is that when you see this bunch of ink here, or this bunch of black pixels here, you know where it came from, or at least, very least, you know you can trace it back. This is not magic. We didn't make it up. All of these things, we went stepwise from a control volume and simple formulas to get here. So I'm going to solve equation 33, this time for time. And if I solve that, the exponential turns into a log, and this is what we get. Time would be temperature at which the target temperature that was 0 degrees minus T infinity that was minus 20, and T naught was the initial temperature that was 6 degrees, and here we have the outside temperature that was minus 20, and tau was our characteristic time, which we know exactly where it comes from and we can calculate it, right? And if we plug and chug the values for water, we get that after we replace and we do these calculations here, we're going to get that the time in which the droplet is flying as a liquid is of the order of half a second. This is a realistic number. And will be more realistic if I got what nozzles they use at Snow Valley, what pressure they use. And with that, from the catalogs of the nozzles, I would know exactly the droplet diameter. And the droplet distribution, we can do so much. All right. Water comes out of the jet and blown by the fan. Half a second later, we have the water start to get its first ice crystal. All right. Because there is a phase change, the equations we have seen so far don't apply, right? The equations for lumped capacitance we have seen were equations in which we said, okay, if there is no phase change, the enthalpy is specific heat times temperature. But now there is a phase change. So what matters to me is not that you memorize the formulas. What matters to me is not that you are able to use formulas. Plug and chug, you will do, right? But what I hope, my best hope, is that you're gonna say, here I have a problem, which I have not seen a formula before, but I have the tools to work this problem out. And the tools are energy balances. In this case, we know that the stage 2, right, during solidification, we know that starts with 0 ice in the droplet and ends up being all ice in the droplet. Anybody can tell me in stage 2 what the change in temperature of the droplet is? I would love to see in the chat somebody suggesting how much the temperature changes in stage 2. Stage 2, the droplet is freezing. Come on, somebody has to tell me that the droplet got the first ice crystal and ends up being all ice. The droplet is losing heat, but it's constant temperature during. Thank you so much for answering. Yes, you knew this. You knew this. You knew this from your thermal class. It's just like a matter of having it handy. Never think difficult. Some things are straightforward. So let's say there is no heat into the droplet because outside is colder. Let's say there is no heat generated. So we have the Q out balances the Q stored. The Q stored is going to be all the latent heat being gone. That is volume of the droplet times density, that essentially is mass of the droplet times the enthalpy of phase change, the latent heat. This is all it is. This is all it is. This is part of week 1, nothing new. And what is the Q out? Well, the Q out is the heat lost by convection. This is week 2. And there's something beautiful here. Because the temperature is constant, I don't need to do an integral anymore. This is awesome. Because the reason we needed to do the differential equation is because the temperature was changing. These things boggles the mind of normal people. But we engineers say, oh, everything is changing with time? Sure. Blah, blah, blah. I end up in a differential equation and I have a fighting chance. In this case, which actually is more difficult because we have solidification, we say, all right, I do the same balance, but because the temperature is constant, I don't need a differential equation. And everybody should be very happy and jumping on their seats now. So when I put these equations, this heat transfer mechanism and heat stored into the original equation, just like we did before, we end up with an equation that is not differential, and we just can't solve for the time of solidification. And you see lots of black pixels here. Don't memorize them. Just know you can get to them with a little bit of knowledge and goodwill. Now I plug and chug the numbers, and I get that is almost 7 seconds. I think I overestimated the size of the droplet. I don't think it takes 7 seconds to cool off. I think the actual droplets are smaller. But if we take this example face value, it says that the droplet comes out of the nozzle at Snow Valley. It's -20, but it was dry, so they need to make snow. The droplet flies for half a second as liquid, starts to freeze, and for a good while is freezing. It's kind of some sort of kind of goopy ice crystal with every time less and less water. And by the time it lands, it better be all frozen. Because once it lands, it doesn't have the wind of the fan and the wind of moving through the air to help the convective cooling. And this is how you make snow. And now you can think so many other things. If you had other liquid, how would it work? How to play with the size of the droplet? If you have a size distribution of the droplets, what would be your distribution of times, right? You can do all those things. I really like this example. So before we finish in this minute, I want to tell you some more about lumped capacitance. And this is amazing thing of lumped capacitance because there is no thermal gradients. The math is very easy. I gave you the example of calculating how long would it take for your car engine to cool down after you park your car. Now, your car engine, I can make a control volume around the block, for example, but the block has pistons and crankshaft and piston rings and a block and a cylinder head, right? All those things made of different materials and with different weights. The beauty of lumped capacitance is each of those parts is at the same temperature. So the heat stored is just, let's say there is no phase changes, is the sum of mass times specific heat of each of those things. So we would have an overall mass times specific heat, right? Mass of the block times specific heat of the block, plus mass of the pistons times specific heat of the pistons, plus mass of the crankshaft times specific heat of the crankshaft. And that's the way we calculate the heat stored using now the same equations we have. And a car engine does look complex. But if you know this, you're going to say no problem. And if you know the weight of the engine and you know how long it takes to cool down, you can even back calculate for what would be the specific heat of your engine, an average specific heat. And then you can do calculations like how long would it take to heat up later on. You can do magic with this, because magic is any sufficiently advanced technology that you don't really understand, other people don't understand, but you do understand. That's why you can do magic. Let's stop here and we continue on Friday. Thank you.